exactly did, but I inserted a new configuration item. By sending 2 more requests, I'm going to make the application allocate the newly inserted configuration item. And this configuration item is just in the size that the object used to be, and it consists of the data that I showed you earlier in the double reference exploit. The first 4 bytes of the new configuration item is the new virtual function table pointer, my fake virtual function table pointer, and the rest of it is my shellcode. Okay, so 1 request, 2nd request. So now when I stop the server, let's see what happens. Yes, my shellcode created a new file called hacked AAAA. So this shellcode could have been anything, and this is my malicious code running on top of the vulnerable IIS 5.1 web server. Okay, so this is the 2nd exploitation technique, and it is called the virtual function table exploitation technique. Sometimes it is hard to find allocations in which you can control the first D-word of these allocations, because usually you'll find allocations that are used in order to create new objects. Each new object will have its own virtual function table pointer. So even if you could control the content of the members of this object, this newly created object, it's sometimes harder to control the first D-word of this new buffer. So in this exploit I have different requirements, but I solve this kind of problem. So using this exploitation technique, I can still exploit by dangling pointers vulnerabilities that in application in which I cannot control the first D-word of the new allocation. In this exploit, I require another thing. I need to be able to control many allocations and deallocation in the applications. For example, a web server, when serving specific web pages that contain specific JavaScript, can control allocations and deallocations of users that browse to this web page. This information can be found, and I was influenced by the paper called Heap Feng Shui in JavaScript, published by Alexander Sotirov. I hope I pronounced the last name right. So this is just an example. I think that in many large enough applications, I can be able to remotely control allocations, but this example shows the fact that when using an application from a remote location, I can control allocations and deallocation. The JavaScript code that runs inside the browser can control the buffer allocations of the browser itself. So, first of all, I'm going to make the application empty the look-aside list of the relevant size. How am I going to do that? I'm going to make the application make many allocations of the same size of buffers of the same size. Then I'm going to allocate a new buffer, make the application allocate a new buffer. Afterwards, I'm going to insert this content into the newly allocated buffer. So I don't have to actually control the first D-word. I can hope it will contain data that when interpreted as code will not be of any kind of trouble for me to execute. But I should be able to control most of the buffer. I put this pointer to a location that has call or jump EAX. This time it is EAX and not ECX, because this buffer is going to be the virtual function table, the new virtual function table of the object. Okay. So the next step will be to deallocate this buffer, and it will be inserted into the lookaside list. You can see the lookaside list in the diagram. Then I'm going to make the application deallocate the object, like I showed you earlier by sending the 3 more requests to the web server as an example. So now I have this object. I have this object that is pointed by a dangling pointer. That when interpreted as an object, it has a virtual function table pointer that points to my fake virtual function table that has and is the third D word pointer to call or jump ECX. So this is actually the code that that is relevant to the third virtual function. So this is the code that runs when I execute a virtual function. So I have the ECX register point to the beginning of the original object. The first assembly line makes EAX point to the beginning of the virtual function table. And the second assembly line actually executes call or jump ECX and makes the application jump right back to the beginning of the virtual function table and execute it as code. This is no longer a virtual function table for the application. This is now code that it will execute. So this is how I execute my shell code in the second exploitation technique. Okay, so now we had 2 exploitation techniques by now, the double reference exploitation technique and the virtual function table exploitation technique. And I'm going to show you the third one. The third exploitation technique is a bit special because it makes it you do not have to have some requirements you had to have in the previous exploitation techniques. And I'm going to first show you the exploitation technique and then talk about what is so special about it. So just like the previous exploitation technique, I'm going to make the application empty the lookaside list. I'm going to do that by making it allocate many buffers of the size of the old object. Then I'm going to make the application allocate 2 buffers of the same size. This can be done just like I showed you, just like I told you earlier, the heap function in JavaScript proves this. This can be done specifically in the situation of browser, but I believe this can be done in many applications and can be controlled remotely in large enough network applications. Then I'm going to insert my shellcode into one of these buffers, make the application actually insert my shellcode. As you remember, I'm searching for controllable content allocations and not just allocations of the same size. Then I'm going to make the application deallocate the buffer that holds my shellcode. Then I'm going to make it deallocate the other buffer I just allocated. And then I'm making it deallocate the original object. So now, look at this diagram. I have the dangling pointer pointing to the beginning of this object that now holds a fake virtual function table pointer that points to a fake virtual function table. That the first function pointer, actually what would be considered as the first virtual function code, is actually my shellcode, the shellcode that I inserted. So what is so special about this exploitation technique? This exploitation technique enables me to exploit dangling pointer vulnerabilities without finding first call or jump ECX or EAX in the application memory. I do not need to count on the fact that I will have these instructions found randomly in the memory. Then I'm going to trigger the bug, make the application execute the virtual function, the first virtual function, and by that run my shell code. Other note, I want to say to you that most of the times the first virtual function will be the destructor, the virtual destructor of the object. And as most good C++ developers know, every object should have a virtual destructor, and by that I can count on the fact that it will probably have a virtual destructor, and this makes this exploitation technique very likely to be used. Game over. Okay, so in the last exploitation technique, the first 4 bytes of the shell code was actually zeros, null, and this is not any problem to me to execute because it just influences the content of what EAX points to. But that's if you can remember, EAX pointed to the virtual function table, I have no problem for it to be changed. Okay. So let's talk a bit about the exploits. We had the double reference exploit. In this exploit, we needed to find the locations in which we can control outside of the application the first D-word of those allocations. We needed to be able to control the new fake virtual function table pointer. And we needed to find inside the application memory call or jump ECX and use it afterwards. We had several more restrictions to the specific address we found. We needed to find another pointer that points to the location where the call or jump ECX was in the memory. And this was the double reference exploit. We had the virtual function table exploit. In this exploit, we needed controllable allocations. We did not actually need to be able to control the first D-word, but we inserted our shellcode in these allocations, and we need to be able to control allocations and deallocations and not just allocations like in the double reference exploit. And we still needed to find the static place in the memory that holds call or jump EAX. And we had the look-aside list exploitation technique, in which we still needed to have controllable allocations. We needed to be able to allocate 2 buffers to insert our shellcode into one of them, and to make the application deallocate both of these buffers. We did not need to find a static location in the memory that holds jump or call ECX or EAX, but we needed to be able to make the application execute the first virtual function, which will usually be the destructor.